Hello, welcome to the Black in Mathematics Association first quarterly webinar for 2025. We do this every quarter. I mean, I think we started this around 2023 and we've been trying to keep up with this. So it's been a very great time of learning. Interestingly, for this month, we'll be talking about a very interesting topic, talking about mathematical, statistical, and machine learning modeling for forecast, for reliable forecasts. That is. So, I mean, you're in for a very great time. So just relax and, have a very great time. We go straight into it. I'll just read out. I'll read out the profile of our guest today, and you can be sure you are here you really like being part of this. All right. So let me go. Dr. Kayode Oshinubi is an infectious disease epidemiology modeler with background in mathematics, data analysis, and computational epidemiology. He studies the transmission of infectious disease, focusing on respiratory infections, mosquito-borne infections, to address public health issues and provide policymakers with solutions. He used several methodologies, including classical statistical methods, machine learning, and mathematical modeling. Is particularly interested in aiding public health authorities in responding to public health emergencies and paving the path for a healthier world. Dr. Oshinubi has over 900 cited. I think it's 1,000. The last time I checked, it's more than 1,000 now. Yeah, I think within the last 1 or 2 weeks, it's over 1,000 now. So we look up to him. So Dr. Kayode Oshinubi has over 1,000 citations. I can say that conveniently, according to Google Scholar, and he has published more than 70 peer-reviewed articles. He has won several grants and fellowships, which have enabled him to be a visiting researcher at Oxford University, Belfield University, and the Helmholtz Center for Infection Research. Currently, he's a researcher at the Northern Arizona University School of Informatics, Computing, and Cyber Systems, where he is building a Bayesian framework for predicting and forecasting spatial models for mosquito population, mosquito-borne disease, and respiratory diseases. Meta-population and population migration are both parts of his modeling paradigm. In addition, he's the chair of Early Career Mathematician, Institute of Mathematics and its Applications, UK, co-chair board for students and early career and member of steering committee, Ecological Forecasting Initiative USA, fellow Heidelberg Laureate Forum, Germany. So we have a big, though he's young, but he has seen a lot and he's still moving. So please, just make up your mind that you're going to have the best of times today, and that is exactly the experience. So over to you, Dr. Kayode Oshinubi. Thank you.
Yeah, thank you, Dr. Dansu, for having me. I'm glad to be here and to speak, to this diverse audience. And I will just, share my screen, and then we dive into what I prepared for today. I know that it is about 2 hours meeting, but yeah, maybe I'll speak for a while, and then I will allow people to ask questions. Today I've been asked to speak about mathematical, statistical, and machine learning modeling for reliable forecasts. Yeah, of course I'm in Northern Arizona. I'm speaking from Northern Arizona this morning. It's still morning here. I know it's afternoon in Nigeria. It's perhaps late in the night in Asia, Australia, and some other part. It depends on where you're joining us today. So the goal of this talk is, to present some mathematical and statistical and machine learning modeling framework. We are going to dive into some of this stuff. And I will demonstrate some different modeling approaches. Some are collaborative work, and one of those research is one of the research in BMA. We have a research arm in Black in Mathematics Association, which I lead, and one of the research I'm going to present that just to showcase what we do in some of the things we do in Black in Mathematics Association. And I also, tell us how do we evaluate a reliable, forecast. So that's what we'll be delving into today. And the first thing is, there's, in the topic today, you saw mathematical statistical model, you saw machine learning modeling. So how is a model created? That's the first question. So it comes with ideas and assumptions. Some of those ideas depends on what you have seen. In today we'll be using more of infectious disease. So I'll be doing more of disease. I know here we have diverse audience that might not be infectious disease modeler, but you can apply some of these ideas to other either business analytics, whatever um, area you chose to, to do forecast or to do modeling, depending on what you want. But I'm optimistic that you are going to learn one or two things from some of the examples in terms of infectious disease I'm going to be doing. So models are created with ideas and assumptions. You assume some stuff in the model. You assume, okay, perhaps you want to have different age group. Okay, what are the age group of interest in this model? What are the age group that are more infected in this model? Or perhaps you want to assume an intervention. So there are a lot of ideas. Then you represent all of these as a mathematical equation, or you can call it a statistical equation. All of these statistics, machine learning, their foundation is mathematical. So that's why I wrote mathematical equation. And then you code them up. You have to use computer code, whether you use Python. I use a lot of R and then little of Python. I know some of you use MATLAB, mathematical, different machine. So you code them up. And that's why today you see that I'm in the School of Informatics, Computing, and Cyber Systems. Like I always tell people, I said it's been long I've been in the Department of Mathematics. I did my PhD in Faculty of Medicine. Some of the visiting research position that I've held, which Dr. Dansu spoke about, like Bill Afed, I was in the Faculty of Biology. In Oxford, I was in Department of Computer Science. In AZI, I was in Department of Biostatistics. So yeah, um, when it comes to modeling, it's kind of multidisciplinary in nature. It's kind of multidisciplinary in nature. Computer code is if it when we say computer code, it's more of computer science. And then you are seeing mathematics there, and you are seeing ideas and assumptions. These ideas and assumptions, like I wrote here now, that models are created by individuals or teams of people. When we say teams of people, it can be both mathematician, biological person, public health, like those of us that are infectious disease modeler. Like the team I belong to now, we have different set of people. Computer science are them, statistician, mathematician, software engineers, because we are trying to build a software. You know, um, public health expert, biologists. So creating a model is kind of you know international. So it can be by an individual. Yeah, you can be an individual. Some of the work I'll be presenting today, some of them, it's just the idea of two of us. Sometimes it's just my own idea, and then I discover somebody, and then we build on it. Sometimes it's an idea of team of people. And like I told you, we'll be looking at what I mean by epi is epidemiology. Epi model that we'll be talking a lot about here is a representation of how we believe a pathogen. Pathogen means disease, is transmits within and among populations. And then we formalize with mathematics equation. And we have a foundation for this epi model, which is I know some of you might have had Bernoulli, but Bernoulli is a French mathematician that developed the foundation that we use in epi model. So we formalize all of this into a mathematical equation. So I want to also briefly dive into some types of models. We have non-spatial models, which is very common, and then we have spatial model. Um, Most of my work, has been on majorly non-spatial model. It is recently I started doing some spatial model analysis, which I'm going to show some of those work. You build spatial model is just a local population. Oh, I'm looking at Lagos, Nigeria. I'm looking at Accra, Ghana, and then that's the only location you are focusing on. So you build an SIR model, or you do an agent-based agent-based population where you have agents. Um, what do I mean by agents here? Agents are like people in that population. We have people that are going to school, people that are going to grocery store, people that are going to their workplace. So those are agents, and they are static. in a local population. So because agent based can also be spatial. That means um spatial in what sense? That I live here. I live in the US. I go to work in Canada. So that you can can be spatial. Or I live here. I go to a grocery store somewhere. So that is a kind of spatial agent. So spatial can be a population can be an agent base, and there can be a partial differential equation. I have a work on that partial differential equation. Like when I was in Oxford, I worked with one of the students I mentored. We use a PD, to formalize spatial, a continuous space and time, to do a modeling framework. So, and then you can have meta population where you use SIR in Korodu, SIR in K2, SIR in Ikeja. Then because you want to model those three populations, and then you are looking at how they are connected. So that's what spatial is. So, and in agent based too, you can set that up, and also we have some places that we call points of interest. Point of interest are where people go for shopping. Point of interest is where people playground where people go and all of that. So these are some kind of a summary of some kind of model that we have. And then we have when we talk about model structure, you are looking at a meta population. So this is an idea of a spatial model where you have an interpopulation. You can see that the interpopulation model, that's the SIR model, is connected to the movement. How people, whether they drive, they take train, they fly. And then you can see that the space, which we label here as a geographic model, that means this place you are considering, okay, I'm considering the United States, I'm considering Japan. So in this formality, there's a current work I'm doing where we are using, movement. We have movement data, real movement data of how people go to work, and then SIR based model, and and then geographic model where we are looking at some counties in the United States, and then we have what we call age structured model. This is a two-type age structure model. I'm also going to demonstrate one work on age structure today. Age structure, you can have like 0 to 18 years of age, 19 to 40, blah blah blah, like that. You can have five different age, but here is just a tool. This is a model I developed, doing my PhD. Just a tool for young and the old, to study, COVID-19 model. So this is a very complex model. It has vaccination, it has a reversible recovering, definitive recovering, high days infectious, um, and today's topic is about mathematics, statistics, machine learning, how you do all of this. So I just want to show a graphical representation of a mix of mathematical model, machine learning, and spatial data statistics. So you have bird, you have mosquitoes. Bird and mosquito, they infect each other, and then mosquito bites, like malaria bites. Though this is not a malaria thing, but this is more of a Western virus. Western virus can be transmitted to birds, so and then you are considering precision and temperature in your model. That is some environmental factors, and then like the arrow you are seeing that is pointing up there, you saw a kind of map. That map is where I am. It's called um, Arizona map, where you cluster some locations there. So, and when you want to cluster, that is, you are doing what you are doing a kind of machine learning, and when you are considering this space, you are doing a kind of spatial data analysis. And when you want to represent all of this transmission, to from mosquito to human, from bird and mosquito to bird, then you are representing the mathematical equation. And then precision and temperature, you are using a kind of time series data, which is part of statistics paradigm or machine learning paradigm. So this shows how you can have a mix of all of this mathematical, statistical, machine learning in your modeling framework. Which this kind of example, I'm going to demonstrate it today. So this first few slides is to show you some of the examples we are still going to delve into. So now we can simulate the model. I showed you on your left there, you can see the ideas mathematical computation, which is the model. So you want to simulate. So there are two things majorly we do in modeling. When we finally develop the model, most time, apart from the mathematical analysis we are going to do, which is not really my own interest. In my own interest is more of simulation and and data fitting, or what we call calibration of the model. You are going to see all of that. So you simulate a scenario A, you simulate a scenario B. There's one example I'm going to show today. We did about like three scenarios or so. So I'm going to show that. So you do a scenario. Look at scenario A. You can see that the disease, the infection starts, slow, and then around the middle of the year, it grows. But look at scenario B. You said that okay, let the infection go faster. So one the infection goes slower, and then one the infection go faster. So these are different, different kind of scenario. And then you can also decide that, okay, which environmental factors drive infection. Like this, just 1 minute ago, I showed you precision and temperature. You can say, okay, you are considering a mosquito-borne disease. Mosquito-borne disease, really, if you want to do anything mosquito, most time they are influenced by environmental factors, whether rainfall, snow depth, precipitation, temperature, all those uh, environmental factors influence, because where there are standing waters, it breeds a lot of mosquitoes. So you want to look at how this environmental factor drive, the infection of disease. So look at this also, there are two scenarios. Factor A, perhaps you just put, rainfall alone, and then factor A and B, you put both, rainfall and temperature. You can see that one did not capture the dots you are seeing is the real data. That's the observed data of the disease. And the lines are the fit. And then those thick thing you are seeing are the error bar, or what we call confidence interval. So because you'll be seeing a lot of this, so I need to explain that. So when you see sometimes I use dots like that, they might be the real data, and then you see a line, those are what your model is predicting, or what your model is forecasting, as the case may be. But I will always explain that. So you can see that for the green, you can see that it didn't really capture the peaks. When the cases were rising, it didn't capture that. But you can see that when you add factor A and B, the model improves. So you have to decide which environmental factor drives, that means and with the way that line look like for factor A and B, it shows that um precipitation and temperature, they influence, they drive the infection. And then you can also say that, what if we impose a certain intervention? Most time when in disease modeling, when you have a lot of cases, you want those cases to go down. Okay, so let's apply intervention. You can see that here we, at some point in the week, we apply intervention, and you can see that the disease start, it goes up, and then it starts, going down. After some time after, you have applied intervention for a while, the disease start, um, you know, stop spreading in the population. So, you can decide what kind of intervention you want to apply, depending on what you have decided. So another question we normally ask, that how is a model made useful for a specific place? Okay, when you build a model, most time we consider, sometimes we generalize, but sometimes we say, okay, some of the work I'll be showing today, they are very specific. They are specific to a particular location. Like Dr. Dawu said, when one of my goal is, to be able to, develop model that will be useful, for a particular location, that they can deploy some interventions, and some resources to to curb the disease. So that begs the question of, how is a model made useful for specifically this Flagstaff? This is where I'm speaking from this morning, where I live. That's the map. So number one, you must collect data and enter them. There must be data. If there are no data, you cannot make, unless you simulate. Simulation is not using real data. Simulation is just, you are trying to mimic real world events. How real world events, how it happens. You have developed model, you just simulate with all those your ideas and assumptions. But when you want to make a model useful for a specific place, you consider, I've not really talked about data collection sense. But now, because you want to make the model useful, you must collect data and enter them so that you can use it. And then the next thing, that model you have developed, you must calibrate them and then refine it. And I'm going to show you how you calibrate. If I don't use the word calibrate, I can use the word fitting, you know. And then sometimes you refine your model, because sometimes your model might not. You are going to see that example. Don't let me delve into that now. So this process of, you collect data, you calibrate, you refine, can lead to a useful model. And what can we do with a useful model? So it begs the question, that what can we do with a useful model? So before I delve into examples, so we are going to see, the general picture of how a model, can be used. So when you calibrate model with data, so you can see those dotted lines are the real data, and then the straight line are what the model predicts. So now you have done a fitting, to the model you have developed. So you've calibrated it, and you need to refine this model. You can see that at some point, the cases are going up, but now your model is not your model no longer match the data. So that means that you need to what? You need to refine your model assumptions. All the ideas, all the assumptions you have created before, so you need to modify it, because now your model is failing at that point. And I'm going to show you, you know, how model fails, and what are the things I'm doing, to tune those models. Some of them I've not published them. I'm still working on it, and I'll show you an example where you know we use a particular method to calibrate a model to data, and then we change the method, and that helped us. And I'll tell you, apart from changing the method, we also change the model assumption, and that improves the model. You are going to see that kind of example, this morning. So, in summary of this first part of the work, to give you a kind of, I'm giving you a kind of background before we delve into, all the mathematical, statistical, machine learning thing, is that this slide answer the question of, you know, how to make a model useful. Number one, you have a data set. This is the summary of what I've been saying. You have a data set. You can have climate data, socioeconomic data, like maybe population size, household size. You can have vectors data. Maybe you have mosquito data, you have the animal data, or whatever, or bird data. You have all of that. Because some of these vectors are drivers of disease. You have that, and then maybe you also have disease count data. And then you develop a model. This is an SIRH type of model. You develop a model, and then you use that model to do a forecast. But before you do a forecast, you must do a fitting, or what we call calibration, which I call here statistical fitting. And I'm going to show you some examples. I think I have about 3 examples of statistical fitting. I'm going to show you non-linear least square method. I'm going to show you MCMC Markov chain Monte Carlo. I'm going to show you ensemble gamma filter, kind of statistical fitting, or you can call them Bayesian method. These are machine learning methods. And then you do a forecast. Forecast, like I showed you, forecast, in the forecast we have temperature and precipitation. I'm going to show you an example of that. We have temperature and precipitation in the forecast. And forecast, you can use a statistical method, which I use, or machine learning method, and then to forecast what will happen in the next few months or few weeks. And then decisions. And that is when models are used. They allocate resources, because you have partnered with public health departments and people that make decisions. They allocate resources, and there's an intervention. So this shows the excuse me. This shows the data fitting and forecasting framework we normally use, which is always very helpful. Um, People want to know what will happen in the future. People want to know, you know, how we can curb the disease. Especially when we experience this COVID-19 pandemic. Okay, so I will take you to about I think I have four examples here. Um, I'll be taking you through those four examples, and about three of them, are collaborative work, my work, and most of this work are not yet published. But the one we I did with BMA recently, we published that. So I'm going to show that will be the last. I think I'm going to show. So this first work is called spatial variation in climate factors predicts predicts spatial variation in mosquito abundance in desert southwest. Desert southwest is where I stay. It's called the desert southwest of the United States. So in this work, we are just doing prediction, no forecast. We just want to predict, and I'm going to tell you the hypothesis we are trying to test. So this is the motivation behind the problem. When you want to develop model, you want to you know do prediction. You have to have a motivation behind what you want to do. Globally, mosquito cause a large burden of disease like yellow fever, Rift Valley virus, Zika virus, and Shiguya virus, dengue and malaria, West Nile virus. And the dot here, this is a global map, and you can see the dot where
Sorry, do
malaria.
you want to take some time off maybe to get water or something?
No, don't worry, I'll be
Are we good?
fine.
Okay, okay.
It's a
All right,
bit
okay.
cold this month. It's a bit cold here this month.
Oh, I see. Okay,
Yeah,
okay.
yeah,
All right.
thank you, Dr. Dansu. Okay, so the red dot, you can see how we have a lot of malaria cases, then Zika in blue, and then you can see dengue. Dengue too is a lot, global. These are driven by mosquitoes. So mosquito is a very, very important, and they continue to emerge and re-emerge, uh, you know, um, across the globe. And sometimes some of these mosquito-borne diseases, they are endemic in some countries. And regional climate. This is a projection from 2019 to about 2080 of how climate we drive the transmission of Aedes mosquitoes. Aedes mosquito majorly cause dengue that I just spoke about some seconds ago. So the blue is lists where it happened across the globe, and then where you see the red, that where we are going to have a lot projected forward. Our climate change, climate. So regional climate is important. So climate change will likely alter large scale distribution patterns of mosquito population and disease. So you can see that for you to to develop a good model for mosquito borne or mosquito you want to predict mosquito population, you have to consider climatic factors, or what we call environmental factors, because they drive mosquito. Like I said earlier, where you have standing waters, it breeds mosquitoes. So that will drive how mosquito population will be in that locality. And then so one of the things I want to test here is that local heterogeneity in weather could explain heterogeneity in mosquito abundances, or what we call mosquito population. So this is the map of uh, Maricopa County, and you can see Phoenix. Phoenix is very popular, and I know some of you will have heard. It's a place that the weather is like Lagos. So you can see that um, temperature, how it changes across this county, this geographical space. So it shows an heterogeneity, that there is an heterogeneity in temperature, there's an heterogeneity in precipitation. So this is the local heterogeneity in weather. So we feel that where you have a lot of precipitation, there should be more mosquitoes. And I'm going to explain what I found. So the problem statement for this work is that we need flexible modeling framework to help us evaluate the role of weather heterogeneities on local mosquito population. So that is the problem we want to account for in this. We want to account for this heterogeneity, differences in climate condition of different localities, and how this drives you know mosquito population in different localities. So the question, the research question is: can spatial variation in climate factors predict spatial variation in mosquitoes abundance or mosquito population? So I have the precipitation curve, precipitation curve of Maricopa County that I'm considering, that I just mentioned. Each line represents ZCTA. ZCTA is the zip code. There's zip code, different zip code location in that county. So I have the precipitation data and what you are seeing on the left is the mosquito population in the different zip codes. So you can see that some zip code have less mosquitoes, and then you can see that also there's also a fluctuation in the precipitation. And so the first thing is that we know there's a large variation in mosquito abundance over space and time, but we don't know how much this is driven by spatial and temporal heterogeneity in climate. We don't know it. We don't know how it is, and that's what we want to prove. So we also know that there's variation in weather, like precipitation that I just showed here. It's not the same for temperature. Temperature, all of this zip code almost, I didn't just show the plot. When I plotted that, this is what we call a kind of data, analysis. You plot your data, you visualize. Visualization of data helps you to identify patterns. That's the essence of visualization of data. It helps you to identify patterns in data. So also, like precision here, over time, can this variation in temperature, explain mosquito population? So that's what I want to test in this one. So we did a way to test this phenomenon, and this work hypothesis is that if we divide this county, this Maricopa County, into sub county, that is clusters. This is where I use, different cluster. I use a clustering algorithm in machine learning algorithm based on similar weather will improve influence of mosquito abundance. So that's the hypothesis I want to test in this work. And this is the whole thing I did in this work. I have precision data. I use machine learning algorithm to cluster. You can see those cluster one, cluster two, the green, the purple, the blue. Where that's on your right. I'm speaking about your right. I use a machine learning algorithm to do the clustering, and then I plot the time series abundance of these clusters, and then I use my mathematical model, which I'm still going to show. So number one, how do we account for heterogeneity weather across the county? Proposed solution: I created a clusters of traps. What do I mean by traps? I'm just interchanging, but I'm going to show you. The traps is also, in Maricopa County, they set traps to take to catch mosquito. Let me just explain that. That's in the next slide. So all this map you are seeing, you can see all these dots are traps, and these traps are located in a zip code, to catch mosquito. And this is what they do. I'll also explain it when I go to one of the other work I'm going to speak about. This is what they do. They set this trap, and every week they go to this trap. They take the mosquitoes. They do the mosquito count. They separate them by male and female, and then we have a collaborator doing all of that. And then they test those mosquitoes of the kind of pathogens they carry, whether it is West Nile dengue, any kind of pathogen they carry. So what you are seeing on this map, the blue line is a river on your left. So it's a river, and then those are mosquito abundance. So uh, the dots on this right is to show you that, okay, what I did in this is that I discovered that there are some 6 locations that have a lot of mosquitoes. So I call them cluster 1, and that's what you see here as red. And I separated those ones. So this is just a manual cluster. I didn't use any machine learning algorithm. And like I told you, that's what you do when you visualize data. So I discovered that 6 of, and then you can see them here. If you go to the right, you see that there are some big dots here. So there are about 6 of them like that. So I call them cluster 1, and the rest of all other locations I call them cluster 2. So, and that's what I wrote here, that okay, that we have about 115 zip code, and then we have 6 that are called I just call them an outlier because they have a lot of mosquitoes. So I call them cluster one. And the remaining 109, I call them, cluster two. So this is just a preliminary analysis of the data I have. So then I developed this mathematical model, you know, which is, you have to, like I explained to you how we develop in the beginning. So the X of T here is our mosquito population, mosquito abundances that I've been talking about. And you can see that I have a function there that has temperature and precipitation there. The precipitation, I calculated it using 30-day accumulated because most time when you look at precipitation data, you have a lot of zeros. Not every time rain falls, so you have a lot of zeros, and they measure that. So you to have a good data. The term in statistics is that to have a very sparse data that you don't want a data that you have a lot of zero. They are not informative when they have a lot of zero. So to have a sparse data, so I aggregated them, and then I divided by 50, to scale them. So I have this VM, the baseline population growth rate, and then I have this mu, which is I fixed the death rate of the mosquito. So the population growth rate, the first term you are seeing in this equation is population, like the births of mosquitoes, and then the last part is like the deaths of mosquitoes. So this climate-driven mechanistic model or mathematical model was used for this work, and then the model fitting, or what we call calibration. I use 2014 to 2016 mosquito population, and then climate data set for that year, and then I use MCMC, Markov chain Monte Carlo algorithm, which is a machine learning algorithm, to do the calibration, and then I did out of sample prediction. This is a statistical. You do a kind of in sample, out of sample. Just or what we call train and test. And I know some of you will have heard of that term, train and test. And then we sum all the clusters and compare the result with county level data and county level prediction. And then, how do you know that this model is good? Like I said, how do you know a forecast is good, or you must have an evaluation metrics. Here I use RMSC. There are some other evaluation metrics which I'm going to talk about. You see that sometimes I will not even use RMSC. I can use R squared. I can use what we call WIS score. So there are different evaluation. You have to evaluate it. So this is our result. The red line, like break line is the real data, and then the model fit is the black line, and then the blue are the confidence interval. So we discover here these are model fields for the county level. So we discover here that our climate force model fits well for the county-wide data. Our model also fits to each cluster well within sample, likely because of the spatial variation. And let me show that result. So you can see this is the cluster that I showed you earlier, and this is the cluster. Each cluster fits, and you can see that the model pretty well, and I'll still tell you this is not too good really, but it's fair. It's fair. It's acceptable. At least the major takeaway here is that it understands the pattern in data, even though it does not capture the data totally, but it understands the patterns in the data, which is important. And then, so this is the comparison. So here I try to compare, the clusters. I sum up the cluster, the real data, and then the observed the observed data. So here the black the black breaking line is the real data, and then the clusters prediction, all of them added together is the red, and then the county prediction, which is the blue, and those are the the error bar. And here we discover that the county prediction is better than the cluster sum prediction. You can see the RMSC here of the county prediction is lower. Lower is good. When it's lower, when RMSC is low, it's good. If it is high, it is not too good. So the model can be useful for. So what we discover here is that the model can be useful for small scale prediction. And then small spatial scale prediction did not improve the countrywide prediction when you aggregate it. Like what I did here, the aggregation did not improve. So the key takeaways from this work is that our model fits to each cluster well within sample, likely because of the spatial variation in average mosquito population sizes. And then the local mosquito population seems to, to similarly respond to weather patterns because we use weather, temperature, and precipitation in this prediction. And then this model can also be useful for small scale, when you want to look at very small scale prediction. And this is the first example I want to show you today. So quickly go to the second example. I want to talk about race and age structure model for RSV. When Dr. Dansu was doing the introduction, I do respiratory bone disease and mosquito bone. Respiratory RSV is a respiratory disease, and in my PhD I did more of COVID and some other collaboration. I've done some other respiratory disease, and also here too I've done flu. Flu is also a respiratory. So I want to show you race and age structure model for RSV dynamics in four corners regions in the United States. So we have some four corner regions. That's the four states in Arizona, Colorado, Utah, and New Mexico. So these are the four corner, and that's the only four corner regions we have in the United States. So where four states meets, these four states they meet somewhere. So yeah, so and they are very interesting state to look at. So RSV disease body in four corner region in the United States. You can see that on your right, you have the age hospitalization rate of RSV in the United States, and you can see that different ages, some have high hospitalization, and some have very low hospitalization. And on your left, you have the race and ethnicity. So you can see that some race, like the blue, that's Alaska native, you can see that they have high RSV. So in this data visualization, we can deduce that that there is variation in different age and different ethnicity of RSV hospitalization in the United States. So in the United States, that we estimated that RSV results to about more than 160,000 hospitalization and 10,000 deaths among adults over 65 years of age. And the Navajo and the White Mountain Apache in these four corner states have a high burden of RSV infection. And RSV is particularly among infants and older adults, and very significant, and is a major cause of hospitalization and death. So, using data visualization techniques, you can see that there is a variation in how RSV hospitalization rate is in terms of age and in terms of race. And I want to investigate this using a mathematical model. And yeah, we'll get into that. And now let me just give you a brief background on how RSV spread. Coughing, sneezing, being in close contact, touching surfaces. It is highly contagious. It's between 3 to 5 days. And some people can spread the virus for weeks. People who don't have symptoms can also spread it. So we have asymptomatic, in the population. So RSV also can live on surface, hard surface, soft surface. So the main point is that RSV is highly contagious and can be spread through contact with infected people and contaminated surface. So this background is to show you that the reason why we are interested in studying this, because it's a burden in the United States. And this is the data we have. I'm going to show just two of these states. I'm not going to show Colorado and New Mexico. So because of time, I want to show you different approaches. So, and we are still in example 2. So this is the data visualization. You'll see that I use a lot of data visualization techniques a lot. So because it's important, it gives you information from the data. So and that must be one of the take home you have. So this is the number of hospitalization based on race in Utah and based on age in Arizona, and these are weekly, reported cases. And you can see, like the purple, that's older population, 75 plus years, they have high hospitalization. And then here you can see that the Alaska native or Alaska Islander, non-Hispanic, they also have high hospitalization uh, rate. So the objective of this work is to model this analysis is just to demonstrate our ability to feed this data for different subpopulation, that's different race and different age in various US states using a Bayesian inference and reveal important disparities or variation in RSV hospitalization. And then I developed this simple model, just a simple model. I don't want to complicate this model for now. So this model is SIH model, very simple mathematical model. We use this model for two age groups, the old and the young, and also for five racial group. We have five racial group here: Hispanic, white, non-Hispanic, black, Alaska, and then Pacific Islander, non-Hispanic. So we use that for five age groups. So I'm just going to show you quickly, because of time, um, two of these fits. So you can see that here we use what we call ensemble gamma theta fitting algorithm. Uh, so I didn't use MCMC in this case because you can see in this model I have a parameter that is time varying. Unlike what I showed you first, that all the parameters are static when I was modeling mosquitoes. But here we have a time varying parameter. So, and I need a very sophisticated algorithm to do that. So to estimate that time varying parameter and all other statistic parameter like alpha, H, and gamma. And here you can see that our model, the dotted lines are the real data, and the red is the older population, the blue is the younger population. You can see that our model pretty fits, the data really well. It captures the dynamics of the data very, very well. This is a very, very good, result for old and adult population. And then I look at the transmission rate, over time for the old and younger population in RSV transmission rate. And also you have to diagnose, the static parameters. How do you diagnose? By plotting histogram, plotting the histogram of all these parameters. I have a parameter H in the model. So I have to, I have a gamma in the model. So I have to look at, how this parameter, are they well distributed? I hope it's not, the reason of this diagnosis, let me explain to you. Whenever you are doing Bayesian, the reason of this diagnosis is to see if the distribution of these parameters are not flat in the ensemble. Here we are using ensemble, so we have number of, in MCMC you say you use chain, but here we use ensemble. So we want to see the distribution of this parameter in the ensemble and see that it is not flat. If it is flat, you have to tune the parameter. So the key takeaway from this work is that this work shows that our fitting routine accurately capture the disparities in the RSV hospitalization and how this disparity can vary across states. In Utah, the model suggests that young people exhibited higher RSV transmission rates. I showed you the transmission rate over time to older individuals throughout the study period. But the contrast is the case in Arizona, where we have, larger older population. Arizona has a lot of larger. They have older population a lot in Arizona. So the phenomenon we were experiencing in Utah was different from what we were experiencing in Arizona. And I can't recall on top of my head of how Colorado and New Mexico is. These are the four corner states this work is all about. Yeah. Don't worry. We'll soon finish. And example 3 is about forecasting. All what I've shown you earlier, they are just fitting. So now I want to show you forecasting routine. So here I want to forecast a Western virus in Maricopa County, where I live here, using climatic factor. And like I told you, whenever you are doing this is a mosquito-borne disease, it's very important you establish some climatic fast factors into your model. You must incorporate them into your model. So the reason why we are doing it is that mosquito-borne disease burden in Maricopa County, this species of which we call queens, keyless queens, mosquitoes, they are found in Maricopa County. There are a lot of them. 80% of this mosquito species, they drive, West Nile virus disease, avian malaria, and SLEV in Maricopa County here. So it carries, a lot of disease. And this is the species of mosquitoes I'll be considering in this work. So they drive, different diseases, and 80% of this, 80% of the Western virus case we have is from this species. Of course, there's another species that has Western virus, but is about 20% or so. And according to the data on CDC, Maricopa County is one of the top counties with Western virus, disease burden. And one of the reasons why we are looking at this is that this this place, and more especially in Arizona, we have a total of 3,000, more than 3,000 human cases. In fact, in 2021 alone, where we have a lot of um, of human cases of this virus, we have more than 1,500 cases in just 2021 alone. And because this disease can lead to a neuroinvasive disease like meningitis, so it is important that we are able to, to predict this disease, and also to forecast, so that our collaborators in the health department in Arizona here, can find our model use to, to prepare for the future. And that's the reason for doing this work. And this is the way Western virus is transmitted from mosquitoes to bird. It can infect human, it can also infect us. In fact, in Germany, they have us data, so they put us in their modeling framework. But yeah, in my model, which I'm still going to show you, I'm only considering bird, mosquitoes, and human, because we have mosquitoes data, we have human data. We don't have bird data. We made some assumptions for bird, and that's what I told you. When you are developing model, you have some assumptions. So I'm going to tell you some of the assumptions we did. So this is how, and human and horse, they are dead end host, but bird is a reservoir host because it can infect when an infected bird, when a mosquito bites an infected bird, they can contract it. So, and you should know that it's only the female mosquitoes that bite. So when I'll still delve into that, don't worry. That's what I want to explain here. So in one of our collaborators is she's the one that collects the data. So what they do is that they put traps, they collect the data once per week, so it's a weekly data. They separate them by sex, male and female. We're interested in the female. Female is the one that bites. Male doesn't bite. So female, so they separate, and then they identify the pathogens they carry. They test those mosquitoes, and then they identify them. But the human data comes from the hospital. So this is the this is the 2021, which is a very important year for us. So we have the abundance data, that's the mosquito abundance data. We have the prevalence, that's the mosquito prevalence data, that's infectious mosquitoes, and then we have the human case data. You can see that there's a lot of cases, about 250 cases. So this slide shows how mosquito prevalence correlates with human cases, because we have very large data set from 2006 till now. But I'm just showing 2006 to 2027 here, just to show you a kind of pattern. And like I said, you will see that I love data visualization a lot, because it helps you to identify patterns. And even without testing the correlation, you can do a correlation using a correlation code to correlate these two data. But we discovered that this mosquito prevalence data, that's the infection mosquito, and the infected human data correlate, and you can see the patterns in data. And like I told you, you can see that for this year, we only have, the highest we have is 30, but in 2021 we have about 250. The highest is 250 in 1 week. So that's why 2021 is very, very important. So mosquito prevalence correlates, human case data. And what my problem here? What question am I trying to answer? There is difficulties with explaining mosquito abundance due to several complexity. You can see the complexity. There's environmental factor, there's human, there's a lot of things embedded in it. Different, species involved, and we must develop a better statistical fitting technique to solve this problem. And we want to forecast mosquito population. What we are trying to do is we want to forecast mosquito population, we want to forecast western virus population, and also our model parameters with temperature and precision as covariate input. That's what we want to really do. But in this talk, like I told you, because of time, and I want to show you several works we are doing, I'm just going to show you the forecast for the mosquito population. And this is the model we developed. You can see the bird, the mosquitoes, and the human. And like I told you, because we don't consider horses, but if you check literatures, you'll see horses, especially researchers in Germany, they do that. And this shows, how mosquitoes infect human, how there's a transmission between bird and human. And we develop the human data based on the data we have, because we have in the data for human from the hospital, we have the infected, we have the hospitalized, we have, and deaths, people that died from the disease. So we have this data, so that because to parameterize this model, we need those data, to parameterize. And that's why we developed this model for human. And then the bird and the mosquito, we made it simple, because essentially the bird, there's less information about the bird. The mosquito, we still have, we have the abundance, and also we have the infection. So we maintain that. But for the bird, we made some assumptions. Essentially, when it comes to the bird population, the bird, we assume uh, a Gaussian type of population growth for bird. So, and this is our statistical fitting and forecasting strategy routine. I know you have seen this picture before, which I showed earlier when I was. So we fit the data. I just used 7 weeks as an example here. We fit the data for 1 year. That's what we did, and then we forecast for another 2 weeks. So we did that every 2 weeks. And let me tell you the reason. I know maybe when it's time for question, you can say, "Oh, why did you do 2 weeks?" Because I'm using temperature and precision. If you go to any of your app, your climate app today, you go there, you see that most time it is just 10 days projected forward. And so because it is only 10 days data, if you go to your iPhone and you look at it, you see that you can only see 10 days ahead of what the climate will be. Yes, I know that you can. There are some other, if you go online, you can see, some people can say, oh, 1 month and all of that. Those ones are not really reliable. But like 10 days of temperature and precision or climate forecast are very reliable. So, and that's why we maintain 2 weeks, and because our data is is 2 weeks. So we did this 2 weeks forward every 2 weeks, and then for like 1 year, 2 weeks, 2 weeks, 2 weeks for 1 year. So 2014 data fitted or 2013 data fitted, and then we forecast for 2014 every 2 weeks. And yeah, this is what I just said now. So we use in this method too, we use ensemble gamma filter method to estimate time varying parameters, and static parameters. We forecast VM of T for 1 week. This VM of T is very important. You saw that in the first example I showed you, it was not a time varying parameter, and you see how, like I said, when you are refining a model. So in this work, we refine the model, and you are going to see the differences in the result. And we grab precision and temperature data for 2 weeks. Then we run our OD mechanism model forward for 2 weeks to forecast about that sample of certainty in VM of T and static parameters to estimate them. And then we repeat the above weekly for 52 weeks. Yeah, so previously I showed you this result, MCMC approach, and then you can see changing the method, changing the model assumption, changing the model parameters, improve the result. So some peaks we could not capture earlier, we were able to capture it. This is MCMC, the first example I showed you, and this ensemble gamma filter approach. So this method fits very well, and it helps us solve some of these places that we could not capture are spring. They are the spring, the spring season of the year. So it helps us to solve the spring problem. So what we did here was, to fit our model 2014, we successfully predict mosquito population and Western viral prevalence of 2014, the abundance, the infectious mosquito population, and the infected human. And then we did for 2021, where we have a whole lot of human cases. And you can see that there are, I showed you that a part in that um, is not it's not good. It's not a good prediction. And what do we mean by a good prediction, which I showed you here, when the model, and also the uncertainty, could capture the data appropriately. So, but regardless, our model, was able to fit the data. And then you can see that the human for 2021 is like an overfit, because it matches the data, you know, too well, too well. So that's what we mean by an overfit. And then you can see that we did for 2024. We don't have human data for 2024, so I can only show the abundance data for 2024. That's the mosquito population, and then the mosquito infectious prevalence data. So we also did that for that. And so we discovered that our fitting techniques has remained robust over effective, robust and effective over a 10-year interval, from 2014 to 2024. And like I told you, you have to diagnose your model parameters. These are the model parameters. I showed you that very big model. So these are all the parameters in it. So we look at, just to look at, the distribution of the parameters in the ensemble, or what we call chains in Markov, Monte Carlo Markov chain. So, and you can see that they are not flat. So just to be sure that our model is working well. And then we did the forecast. So these are forecasts for 2014 for 1 week ahead. I'm going to show you two results for forecast if you just do 1 week and then 2 weeks. So you can see that some are good. And let me explain here. The red is the real data for 2014, and then the blue dot is the forecast, and the lines are the error bars. So when you say it is good, that means the error bars or the dot, lies on top the real data. So you can see, yes, where it is not good, you can see that nothing falls on the real data. That is a very not too good forecast. But pretty well, you can see that most of the parts in this time series, our forecasting routine was pretty good. And then these 2 weeks, some parts were not good, and some were really good. And this is a one-to-one comparison. And here, like I told you, when you want to say that is your forecast good, you have to have an evaluation metric. So I use R square here to evaluate 2014. I didn't show you the 2015, but just to maximize time. You can see that both are almost 0.7. That's 70% accuracy, which is good. Comparing our forecast with the real data using a one-to-one technique. So this technique is a one-to-one. We call it a one-to-one graph of forecasted versus actual values. And then we also want to compare. That was our own routine. We want to compare with other statistical machine learning techniques. So the first one is GNM, generalized linear method. And you can see that for 2014, it was even the R square was near 0, and we had about 0.68. So we discovered that our method performed better than others. For 2015, it's about 0.34, and we have about 0.7 in our own method. So you can see that our method is good. We have confidence in our method. And then we also use GAM. GAM is generalized additive method. It's also a machine learning technique. So we use GAM for our forecasting routine. And then we discovered that for 2014, it's about 0.4, where we have about 0.7. And then for 2015 is 0.3, where we have about 0.7. So And this is the second method we compare with to say that, okay, our forecast is good. And then this is the last one. It's called a naive, a naive kind of method. Um, so this naive method for 2040 is about 0.3, whereas ours is about 0.7. And then for 2015 is 0.4, whereas ours is about 0.7. So in all the three methods we want to compare our forecast, we compared our forecast method with our method was perform better. And then the key takeaways from this work, we are almost done, is that our modeling and forecasting framework successfully captured seasonal variation in mosquitoes population and West Nile virus prevalence throughout the decade-long data set. And we successfully use ensemble Kamafita to fit mosquito abundance, West Nile virus prevalence, and incorporate the effects of climate. And despite potential changes in environmental condition, data quality, and underlying dynamics over the decade, our method constantly captured the key trends and variations in mosquito abundance. And our fitting approach will be useful for predicting human risk of mosquito-borne disease. We compared our old data and with recent data fitting and forecasting. This long-term consistency allied the reliability and adaptability of our approach, making it a valuable tool for forecasting and decision making in mosquito-borne disease. And our preliminary method provides fairly accurate 2 weeks ahead forecast of mosquito abundance in Maricopa County. Our findings underscore the value of integrating climate data, adaptive filtering techniques to address forecasting challenges, ultimately enabling more effective response to emerging or re-emerging pathogens of mosquito-borne disease, which can be driven by human behavior to become a pandemic. And this is the last example, which is the work we did in BMA, which was published early this year. I think it was published in January or February. So this is a very recent work. It's online. So this one is online. So all of this, the three work I presented earlier, one of it is going to be, I'm going to submit that for publication this month, and then perhaps for you to read more about it, you'll be able to see. The other one I'm still writing. The one on RSV, I'm just getting a grant to do that work. In the United States, most time you don't do a work without having a grant to back it up. So I'm just getting a grant to do that work. So the RSV work, you might not see it online till maybe end of this year. Maybe by the end of this year, we should be online. So here we investigate MPOS strain dynamics using computational and data-driven approaches. This is a joint work with some, I don't know, maybe some of them are online here, with Dr. Dansu, who was the first author. Who is the first author? And I can't remember all other authors on that paper. What motivated us to do this work is that we discovered that MPOS are different, strain. And one of those is called, the strains are called Clade 1 and Clade 2. So MPOS map reveals countries with Clade 1 risk. So, and that's what you can see here, where you see places that are like orange, they've reported Clade 1 MPOS. Those that are in yellow, there's a potential that they are going to get MPOX. So these are some of the information we wanted to test. So the MPOX outbreak, particularly in Africa, present a signal health body with over 100,000 cases reported in 122 countries. MPOX with two main clades or two main strains has distinct geographic distribution. Clade 1 is endemic in Central Africa, while Clade 2 is endemic in West Africa, with a recent Clade 2B outbreak causing a global spread. The DRC, Democratic Republic of Congo, alone has seen more than 15,000 MPOX cases of all clades and more than 500 deaths since the start of 2024 alone, with over 96% of all global cases and deaths occurring in DRC. And this is how MPOX spread. The virus infected animals, then they can scratch or bite person, and then there can be a transmission from person to person from sex. We have some papers also in BMA that talk about sex was incorporated into this model, into that model, not this one. Hugging, kissing, massage, and day-to-day contact or sharing contaminated, and it also can be transmitted from mother to child. So this is how. So our problem statement is that we want to study mpox strain in different countries. You can see that the first map I showed, it happens in different countries. That's a geographical distribution. So using a mathematical model that incorporates multiple transmission pathways and strain specific dynamics. So we developed this mathematical model, and I1 and I2 here is showing the infection of different clad, susceptible, exposed, hospitalized, recovered, and then for the mammals, or for animals, we have just susceptible and infected. This modeling framework has two kind of, and then sometimes in research work, by some other researchers in BMA, they only consider human to human transmission. And then we also discovered that there's a lot of, in LGBTQ, there's a lot of transmission of mpox. So that was also investigated by some team, in BMA. But I'm just showing this work, on mpox, that I was part of that group that did this work. And so this is the data we have. We are considering 4 countries: Spain, Italy, Nigeria, DRC. And you see the reason why we are considering this country, because they are exporting some of these cases from Africa to Europe. If you read about mpox, you see that. So this is the data we are considering over time. Is a weekly reported cases, over time in DRC, Nigeria, and Italy, Spain. And so this is the result of the data fitting, which we use a nonlinear least square method. Here we are evaluating the best model, and also here we no forecast. We are just doing a prediction, a fitting routine, and then we are going to say that, okay, which of these fitting routine is good, captures the data well. So, and we are using RMSE here to evaluate that. And these are fitting routine. This is not a bad fitting. The RMSE are not, varies across country. Our modeling framework was able to capture some country better. And here, the best is 8.9, which is Italy, with the RMSE score here. And then we did some statistical fitting. I've talked about generalized linear method. This fitting is not too good, because you can see that previously we have Italy of about 7 point something. Now we have about 10.7. So which is not good. This fitting is not good. We wanted to compare this mathematical fitting with normal machine learning technique. But GAM provided the best fit for the observed data. You can see that we have about 6.2 1 year for Italy. So this is good, and you can see that the fitting capture a whole lot of dynamics in the data. Look at Congo. You can see the pattern of going up and down. Goes up, goes down. This generalized additive model was able to to capture it. So for our fitting, the statistical fitting does better than the mathematical and the other statistical fitting. So GAM does very well. So we also did some scenario simulation. I talked about scenario. So like I told you, all what I talked when I was introducing this talk, I wanted to demonstrate it. So in this work, we did a scenario simulation. And the first scenario we did was, okay, what is the impact of Cloud 1 and Cloud 2 across this country? And so you should focus more on the black, and this parameter tutor differentiate the class. So we wanted to test how is it predominant in Italy, in Spain, in Nigeria, also there. So you focus more on the black line, and notably, the predominance of Cloud 2 infection shows a higher mpox failure compared to other selected country. So we discovered that Cloud 2, shows is more predominant in those countries. Another scenario we tested, sorry, I'll be moving fast so that we can round up, because I've been speaking for about more than an hour. Is that we also want another scenario too we did was that we want to vary the transmission rate. Transmission rate is very important in modeling infectious disease. So we wanted to vary the transmission rate, for Clade 1 strain in the population. How does the transmission rate behave? So, and what we discover is that increasing the effective transition rate significantly amplifies the spread of mpox clade 1, especially in DRC, Nigeria, and Italy, leading to exponential growth in infection and higher basic reproduction number. In contrast, Spain shows a limited response to increased contact rate, suggesting clade 2 remains dominant there, and it is clade 2 that is spreading towards towards Europe. And then we wanted to we also want to vary, this contact rate, transition rate, for class 2. And what we observed that the simulation shows that increasing the effective contact rate leads to a sharp decline in mpox class 2 in Italy and DRC and Nigeria. In Spain, it causes a dramatic surge in cases if we increase the transmission rate. And this shows that if these cases, and it's possible for you to import to Spain, they must be wary of if you have a lot of contact of class 2 in Spain. And the key takeaways from this was that the result highlighted that in Spain the prevalence of class 2 mpox could escalate dramatically if nothing is done. A similar trend was also observed for class 1 mpox in Italy. Should class 1 spread into the country, and which is possible because there's a lot of illegal immigration in Italy. People go through water. So class 1 is not yet in Italy, but if it's that's there, it's going to cause a whole lot of problems. So that's what we discovered. The signal risk of widespread transmission could occur in DRC if the contact remains unchecked. So the Democratic Republic of Congo, and this is what has happened in real life, that they normally have a lot of cases. So if it is not checked, they are going to, have. And our findings emphasize the critical need for immediate and comprehensive mitigation strategies to curtail the spread of mpox in Spain, in Italy, and in DRC. And with that, I hope I've been able to show some of the mathematical and statistical modeling and machine learning um, for a reliable forecast and some of the work we have done over the years. So thank you very much for listening. And I want to stop talking.
Wow, this is serious. Thank you so much for that intensive. I mean, people are clapping and showing you love. Thank you so much. That was serious. Like it was. I'm looking for the right word for it. It was high powered. Thankfully, we have it on record, so we can always refer to it from time to time. Thanks a lot for this. So, of course, it's time for questions. So, if you have questions, you're free to type them in the chat, or if you want to talk, you are free to unmute your mic. So, but first of all, you want to signify by raising your hand so I can recognize you, and then you ask your question. Okay, yeah, that's fast. Thank you. I have two people. Oh, okay. I have Dr. Minkal Mohammed and Damila Defrede. So I'll take Dr. Minkal first. Please go ahead.
I feel my head swelling when you said Dr. Mika. I'm not doctor actually.
Yeah, I have a policy. That's how I do it. So just receive it if you want it.
Thank you. I appreciate it. Honestly, I'm gonna say, Doctor, thank you so much for that presentation. My question is, when you talk about in your first slide, when you talk about those special non-special this, I don't know if you can scroll to that your first slide there. Yeah. So when you then you said that for the non-special model, I think at some point you are talking about do you use like ordinary differential equations or just partial differential equations?
Ordinary. You use partial differential equation in spatial. You don't use that for non spatial. PDs in disease dynamics is continuous in time and is more of a diffusion technique. So, and when you talk about diffusion, you are going from one place to another. So, for non-spatial, we use more of ODE, and then also you have statistical. You can see some of these GLM that I showed, GAM, they are just statistical, model, simple linear model or non-linear model, as the case may be. So that's what you use for non-spatial.
No, thank you. Appreciate it.
Okay, so that tells us that ODE is just for time and PDEs are for space and time. So if you are talking space and time diffusion, you go for PDEs. Great question. Dr. Dafrede Damilola.
All right. Good afternoon. Thank you so much,
Yeah.
Dr. Emmanuel. Yeah. So it's been an amazing webinar, so to speak. My notes are actually full, and I think I would say that I'm really honored that you took this class. So, and my mind is kind of inquisitive right now. So one of the questions I'm actually curious about is that. I understand that what we're talking about here is disease and trying to build models to see, to make some few predictions. In my own case, I've been working on something similar. And one of the things I've also been curious about is that what model will work on predictive measures in health outcomes. And one thing I've been curious about has been neurological disorder. So, in my wild thought, I know I took some courses in computer science, things like discrete and continuous variations, and things like that. So, I've been curious about, will there be a combination of models to see, to determine why and how to address some neurological issue when it comes to modeling? And how do I go about it? Because most neurological issues are not, you can't, it's more like they're like things that you need to manage. Like in my head now, I'm looking at something in like a continuous issue whereby you are just growing into recovery. What's your take, doctor? How do I approach this? And if it's something you think
Yeah,
you
the
have done
first thing I'll
before.
ask you is that do you have data on this thing? Do you have data? That's the first question.
Oh, very well. So I'm currently working with a medical doctor, and the person is actually, I, I can't simulate any data because the data I'm seeing online are not actually fair enough. So how I wanted to approach it was to see how people were actually asking questions on those concerns, maybe from Google, search, probably they're searching for issues on that case. Probably I could find hints on that data. So I'm also working neatly with a neuro doctor and seeing how
Yeah,
this can
I'm
be
happy.
done.
Yeah, I'm happy you are doing that. That you are working with a doctor. Number one, like I said in this, I said models are created by individuals or teams. You have to understand the disease, like neurological disorder you want to look at. You have to understand it. Before I present models, you see that I will give a kind of background information about the disease, how it is spread, how it is transmitted. So you have to understand the dynamics of that disease. Whatever thing, so you have to have the biological information. Uh-huh. And you also have to decide what are the factors that influence this neurological disorder. Is it because maybe they are staying in rural area, they don't have access to health? So there's a point I talk about socioeconomic, climate, environment. So you have to look at, does this influence um this disease? What all these disorders they have, perhaps because they don't have good health quality, good way of life around that place. So you have to take a look at all of that. So like I showed in this talk, you see that I love to look at patterns in data. I love to. So when you have a data, look at the pattern in data. And another thing we normally do, we don't also know, is that we normally look at literatures a lot. What's happening in this field? What are they doing? What kind of assumptions are they? What have people done? So you must look at all of that, and then try to conceptualize all of this into a kind of mathematical or whatever. It's not compulsory to use mathematical. You can use statistical framework, or machine learning framework to do your modeling. So you have to look at what is out there, your continual discussion with that doctor, you have to look at the data, and then with that you can come up with simple model. Like I always tell people, start with simple model, and that's what you see I did today. I moved from simple to complex. You see that I started with a simple OD for the first one, RSV, then I go to RSV, that just a simple model, and then I went to a very big model that has 3 species, human, bird, and mosquito, and then I moved to another one that just have mammals and humans. So in modeling, just start small. Maybe a simple exponential model, or a linear or non-linear model, or a discrete model can do. Just start without something simple before you start building up, building more on whatever assumptions you want to do. So you must ensure that you understand the disease properly, this neurological disorder. I think I've seen some of those. They do a lot of a kind of measurements and all of that. I think I've seen, I like I told you, my PhD was, I was in Faculty of Medicine, so I was with medical people. So my big building like that. So I was with a lot of men, and some of them were doing this neurological stuff, and I know that they use a machine to take some kind of measure which they record and all of that. So I hope that is helpful.
It was really helpful. It was really helpful. Thank you very much. Really appreciate it.
Yeah, I think you need to talk more with mathematicians, statisticians, and mathematics. Okay, I think you're into more machine learning already. So we are here for you. So if you need to talk more, we are always available. Thank you so much for the insightful question. Dr. Tijani Ahmad Sulaiman, the floor is yours.
Thank you. Really good talk. Unfortunately, I missed most of it. Hopefully, we get recordings or slides.
Yeah, I'll send the recording to everybody who signed up.
Perfect. Sure. So I just have a question on the MPOX model. The last plots showing differences in trajectory in countries. So I just want to ask, what do you think is driving the difference that you're seeing in Spain in terms of the biology compared to what we're seeing in other countries? Thank you.
This last plot of varying the contact rate, if I'm correct.
Yeah. So I'm seeing an increase in Spain compared to other countries.
What is currently going on in terms of mpox, and the reason why you are seeing a kind of increase in Europe is because there are new reported cases, influx, and these cases are imported cases, into this into Europe, and also even in the United States. And that's why, like I said, there are 2 major clans, but we now have A and B, to categorize the ones that are going to Europe and then also into the United States. So why you are seeing that increase is because these are imported cases, and then because these places are tourist destination, and that's why you are seeing this increase from Africa to Europe. And like I said, in one of the takeaways from this work was that we fear that for Italy, because Italy has a lot of illegal, and then and they are coming from Africa. I don't want to paint us really bad, but I know we see this thing every day. Is through water and all of that. If they import those cases, we fear that Italy is going to also have a whole lot of cases. So that is what is really driving the transmission in Europe. And another thing I personally discover is that when people don't really, they are not prepared. They're not prepared for some of these diseases. They don't really understand. They don't have a lot of understanding about this disease. It shakes them. At the beginning. So some of the cases we are seeing in the US and also in Europe is due to the fact that they are not prepared to. They don't expect that mpox will come, and and they don't really have. They are just trying to now understand the disease. And now there's a drive in terms of vaccination, and that's helping to lower the spread. Another thing, which another paper we did in BMA, there's a lot of sexual transmission in Europe and in the US. That is also driving the spread of the disease in terms of men having sex with men, especially men having sex with men, which we have studied in BMA. It's driving the disease a whole lot in this Europe and the United States. Yeah.
Thank you so much for the great question, and thank you, Dr. Kayode, for the answer. So, like you pointed out, two driving factors for mpox will be that men sleeping with men, men having sex with men, and maybe irregular immigration, and it's not easy to vet people who are coming in through irregular immigration. So that can be some issue. Thank you so much for the insight. Dr. Oluwafemi Samson Olagbami, thanks for coming back. Please go ahead with your question.
Okay, Doctor, thank you very much for the privilege.
Yes, sir.
Dr. Kayode, thank you so much for the time.
Do you want to raise your voice a bit? We can barely hear you.
Can you hear me now?
It's better.
Okay, yeah. So I was appreciating you, sir. Thank you, sir, for the privilege, sir. So then also, Dr. Kayode, thank you very much, sir, for the time spent to prepare this. My question is around the first example presented. So there's always an issue around when we do model fitting, and based on our fitting, which is more of statistical, and maybe we are using a mechanistic model, more like a deterministic model. So we are using it, we are fitting our model, that kind of model, to data. So we have some estimates that we get, and most of the time we don't always, after getting some certain estimates, we expect that those estimates should be helpful to be able to recreate that kind of what we have in data. And so sometimes we don't really have that reproducibility of what exactly, based on the estimate and based on the fit. I don't know if you have a comment around that, sir. And
Yes.
for the work also, sorry, sir, and also for the work also, based on the estimates, we can also way forward, like see scenarios, like what happens when this happen, what happen when exactly when this happen. Could we test for scenarios much more effectively that could inform policy?
Yeah, I agree with you that sometimes I think I showed an example where the model failed.
Yes, sir.
Sometimes, like this slide I want this slide that I'm showing you now. That's why we say you should refine, you should tune your model. And I showed you an example where I use MCMC and then I use
Yes, sir.
ensemble gamma filter, and you can see that helps. And also, not only that change, not the method alone change, I also change a parameter, a VM parameter, a baseline population growth, to a time varying parameter that it should not be static truth. So sometimes the mistake we make is that some of these parameters are not supposed to be static. Let me tell you the truth.
True.
When it comes to transmission should not be static over time.
True, sir.
So when we assume that it's static, we are just doing that assumption. It's not right, really, in the real sense. Yeah, but of course we can say, okay, yeah, it's acceptable. But in reality, transmission is not static. So our transmission is supposed to vary over time. Because that drives infection. And infection curve is not static over time. So we have to fine-tune our assumptions, refine the model, in such a way that, like the mosquito-borne disease, at some point I had to change the bite rate. It's bite. Bite also influences transmission. I had to change it to a time varying parameter at some point when I was refining the model. So, and then sometimes based on the data or based on what you are working with, there's seasonality in that data, especially when it comes to mosquito. So you have to account for that seasonality. Either you do a cause sign function, cause and sign function, to account for the seasonality, or you try to include some climate variables or climate time series data. So I agree with you. So when we discover that, you can see that the picture here that the model fails, when the case was going.
Yes, sir. Yes, sir.
And yeah, and it means that it's not capturing that. So
Mm.
but look at in the case where I showed two scenarios. In the case where you now use perhaps an environmental factors, you can see that the model was able to capture, and in this case, the factor A didn't capture that. So you must be able to to fine tune your model, to but of course you must also avoid overfitting, and yeah, you must avoid that. You must avoid this total lineup. And I showed that, and I showed you here that there is, like, I showed you that one of my work that is is the case of overfitting. Year
Yeah.
where for 2021 where we have for the human case is overfitting, because it's
Mm.
like the model and the data are lining up together, and which should not really be. So,
True.
and here is a case where you tune the model. You were not capturing peaks before, but here I changed one of the static parameter to a time varying parameter. I changed the methodology, and then
Mm.
it improved, the result. So yeah, so that's a different thing. You must learn that you must always fine tune your model to to demonstrate real work. Uh, but you can't have a perfect model, but you can have a useful model.
Yes, sir.
So you can't have a perfect model because there are a lot of factors that goes into disease spread. Mm. And sometimes you have to also account for perhaps maybe uh, household size.
Mm.
Different household size, the disease will transmit is different. A house of 10, a house of two, So in fact, there's a work somebody presented a few days ago. Household size, that data set influences the spread of disease a whole lot. A whole lot. So yeah.
All right, sir. So then, sorry, sir. Lastly, my last question will be on one of the models you presented. So since um you're doing a lot of more like a lot of quantitative analysis.
Yeah.
So I think the model for, I think, is it RSV now, where you
Yeah.
considered SE and hospitalized. So I feel it might, maybe because of the exposure or what I've read a bit, there's a lot of simplification around that, which sometimes might lose some vital information. So, but really, I've not worked on that before, so I don't know what exactly the biology is saying as to.
Yes. This is the model for the RSV. You are right. Like I told you, I'm considering age groups. I'm considering racial.
Okay.
You, you don't want the compartment to be too much.
Yeah,
So why
yeah.
not just capture? And let me tell you this: when it comes to respiratory disease, the most important data and the data you have for this is hospitalization. People don't
Oh, yeah,
really you can't account for infected.
yeah.
You don't have data for infected because when you have flu, most people don't go to the hospital. But it is only those that go to the hospital that is reported.
Okay.
So you have a lot of unreported cases in that population. So that's why you see that. Yeah, I'm talking about. The data I have here is hospitalization data. I'm not talking about infected. That's all case data. No, I have hospitalization data. So if I have that in my model, it's sufficient enough because that's what that's the data I have to fit, the model. Of course, I agree with you. You can, asymptomatic, symptomatic, reported or reported. You can account for that. You can expand this model,
Okay.
and there are very few deaths. You can even put death there. There are very few. So making it simple, like I said, make it simple. If the simple model can capture key dynamics, it's fine. But if not, yeah, you can, you can, you can. It's a respiratory disease, so hospitalized is key for RSV. In this case, yeah. Unlike RSV is different from COVID, and yeah, it's different from COVID. COVID then, they were reporting the case, and then we have hospitalized people, and then we have IC, people that go to IC. We have those kind of data. You have to account for that in your population. Yeah, and what I would have think you should suggest that this model should at least perhaps have a vaccination compartment because people are being vaccinated. Every flu season, you take shots. Yeah. Very few people for RSV, not a lot, but people get vaccine, really. But like flu, every flu season, I've taken my flu shot for this flu season, I took that in October. So every year you go for flu shot. But if this model is I'm considering flu, normally you should consider vaccination in the compartment. So I think that's the only major thing that is really missing. But I'm considering 2 age group, I'm considering 5 racial group. I don't want to complicate it. But of course, I agree with you. I'm still going to expand. This work is not yet published, so I'm still going to expand this modeling. This will not be my final model. This is just to test. I just want to account for the disparity in age and also in this different racial group.
All right, thank you very much. Why? Because why I say that is because the interest here more is quantitative. You have more info. There will be a lot of information that you'll be given from the model, as compared to why people we don't do complex modeling in terms of the qualitative analysis aspect of when you have more.
And for me, I'm not interested in the qualitative anyway.
That's it.
You can see that I didn't show any
any
boundedness, any stability, any uniqueness.
It's quantitative.
So I'm more interested in the qualitative. And I'm in a quantitative lab. They are not interested in all of that.
Yeah.
Even though I'm still a mathematician, but they are not interested in all those mathematical analysis.
Yeah, I think we've come to that point where math has to really make sense, not math for the sake of math like we had in the 1800s or so.
It makes sense because it is the foundation for the qualitative. You do the math. The math has started it. So you need the math equation, and I think that's sufficient enough to show that math, rather than doing stability, uniqueness, where people don't even understand what is going on there.
All right, so we'll go for our last 3 comments. So I'll take not any other one after this one. So I'll go for my namesake next, Dr. Ludaire Emmanuel. The floor is yours. Please, if you can take a minute. Oh, David. Okay. I think I'll concede for David. Thank you.
Okay. Thank you, Doctor. And thank you to Dr. Kayode, our very own leader. Well done, sir. Nice presentation. All right, quickly. I think I want to talk on the second paper where you were comparing 2 algorithm, the clustering and the prediction, and you use the mean square error as the metrics, right? And I think the prediction algorithm performed better than the cost clustering. So my question is mean square error sufficient for a clustering algorithm? Is it a perfect metrics for a clustering algorithm?
Yeah, let me say that number one, some of these measure you can see at some point I use R squared. Some of these measurements they are not perfect, but they are still good. They are still informative. The error in the model. This is error to show that that is far from the real data. That's what it shows. And it's simply is informative. In fact, sometimes you don't need to do this measurement by the plot. Dr. Dansu, you can, when you see the real data and the predicted, looking at the plot, you know that this is better, this is not so good. So, but let me say one thing: when you are doing forecast, the best metric should be WIS. It's called weighted interval score. Do you know why? The reason why we call that best is because it incorporates the uncertainty in the model. That is all those error bars you are saying. Those shaded portion. WIS allows you to incorporate them so that both the uncertainty and the median, we are plotting the median, and the median, are in the calculation of your metrics. So for forecast, if you look at most forecast paper, they use WIs, which is very good. When you do MCMC, I didn't present the WIC. Let me tell you this. I have the WIC. I'm not in the paper that which I'm going to submit for this work that you're looking at in this month. In that paper I didn't just put the WIC. I present the RMSC and also the WIC. The WIC. WIC also incorporates the uncertainty in the model prediction, which is very good. So for this, WIC is the best in a real sense. In terms of the machine learning and the statistics, WIC is the best metrics, to show. But RMSC and R square, we shouldn't throw them away. They are also good. In fact, we also have AIC, we also have BIC, but R square and RMSC are something that is an old metrics, and we shouldn't forget our ancient landmark, like the Bible put it, So we must hold on to all those previous, all those old metrics. So RMS is not bad, but the best metric in this case is what we call WAIC. I just forgot the full meaning of WAIC. Sorry, I think I can get that for you. So WAIC.
Don't worry, I'll get it. Don't add that to your stress. I'll get it while the next person is asking their question. So over to Uniben, Dr. David Aigbodion.
All right. Good afternoon. So good afternoon, Dr. Kayode. I want to say I'm really privileged to have listened to everything that you have been saying, and it was really a wonderful talk, and everything about the modeling and the disease spread forecast and all that. It was a really nice talk. Well, my question is does BMA, does it have a community that I can join and get more of these informations? I really want to get more of this information. Like this is what I need in my life right now. So I really want to get more on mathematical information and modeling and all that. So is there a community where I can get this stuff quite regularly?
Yeah, of course. Before I answer that, I've put the meaning of WIC in the chat, so Emmanuel can check that.
Thank you, sir.
Put it. Yeah, we have a community. But David, what's your background? Are you also a mathematician or a statistician?
Okay, I'm an engineer, but I'm a math enthusiast.
Okay. Yeah, we have a website. Maybe Dr. Dansu, please pull up the website in the chat. We have a website. You can join Black in Mathematics Association. If you are interested in research arm, you can join any of the research arm. We have the applied mathematics research arm and we have the pure mathematics. So two basically. And then, but in the applied, we have sub projects. We have sub projects. We have some people looking at social ecological modeling, and then we have some people looking at different infectious diseases. So we have about almost 5-6 groups, subgroups in applied mathematics. So you can. So that's the community we have.
Yeah, the website is right there, and from there you can join our. We have a community on Telegram, and as now you can then go into the groups from there. If you show your enthusiasm, your interest. So, but start with the website, register to be a member, and we can take it up from there.
All right, so thank you very much, sir.
There's a question in the chat. Maybe we should take that one.
Yes, that's what I'm going to read next. It's from Ruth Aleshinloye, of course, Dr. Ruth Aleshinloye. So thank you for today's session. Even though I'm still a recent graduate, the models look so big. I still learned some new things, I believe. To the facilitator of the meeting, thank you, and to the amazing speaker, thank you, sir. So my question is on something else. I'm interested in machine learning and statistics. I need advice on which part to venture into. Thank you, sir. I hold a BS in mathematics.
Yeah, I read that question and I don't know. as you journey in life, sometimes you start developing interest in some things. But I think one thing you can do is to perhaps be a machine learning engineer. Is a very good, machine learning engineer. They don't only write code; they develop pipelines on how all this machine learning. So that means you'll be good. You must be good with GitHub, and some other things. So if I'm to advise, I think the path I would advise you to venture into is to be a machine learning engineer, and the market is good. So if I'm to speak from the perspective of the market, so you'll be good with not only coding, you also help them to develop some machine learning architecture, machine learning pipelines. So if I'm to advise you, you can just, it's a very broad area. So I think machine learning engineer is not it's not bad. You can venture into that, but you must start simple. That is, start by learning R or Python. Start by brush up your statistics and mathematics. The foundation of machine learning is in linear algebra. So, and that's mathematics. So your maths and sciences, I'm glad you have a BS in mathematics. So maths and sciences must be strong, and then from there you take it up from there. You write codes, and then you develop from there.
Thank you so much for the answer. I think to add to that, as a mathematician, right, these days you can find MSc and PhD programs in data science and all that. So data science and machine learning. So you can actually go for that and just go on from there. So again, I've put the link to our website, blackinmaths.org. So it's there. You can click on that, sign up to be a member, and then you can be part of our community. I also put the YouTube link channel for BMA, so you can sign up to our YouTube link, because all the videos, this video is going up there, and the ones we've had in the past, you can also find this. So please go ahead, subscribe, so you don't miss out on any of our webinars in the past. So our time is fast spent, but I'd like to round off with this last question. So I've picked words like prediction, forecast, and projection. What do you have to say about this, Dr. Kayode?
Okay, yeah. Prediction, forecast, and projection.
And projection,
yeah. Sometimes people still see, they still use prediction and forecast or projection interchangeably. But in the real sense, prediction is that you are predicting what happened, but forecast is you are predicting ahead. So people can say predicting, forward prediction, and predicting ahead. So sometimes when they say that, then you are forecasting. Projection too is also like forecast. You are projecting forward, or So these three words, they are used interchangeably. But if you want to be really specific, you use prediction when you are just doing known things. You are just, or fitting. You are just, but when you are looking ahead, you say you forecast or you project. You do a kind of projection. So these are the way, but they have a kind of relationship.
How far ahead is reliable enough for a forecast?
For me, I had an argument with someone. For me, it's 1 to 4 weeks, and that's the standard for us, and from what I've seen in papers. Because most time when it's more than that, it fails. It's not really accurate. And when you look at forecasting challenge, there are a lot of forecast challenge globally in Europe. You see that's the standard, 1 to 4 weeks ahead. So for me, I strongly believe in that.
So it will be like projection is taking liberty, because we see data like they'll tell you in 2050, Nigeria will have a higher population than America, so whatever. So that's like you're taking liberty. Of course, nobody can really that, right?
Mm.
Okay.
Of course, yeah. Like what I presented here. So this is a kind of projection. Can you see this? So this is a
Yes.
kind of projection. So they are projecting, and projection sometimes is like you are assuming, even though you are still using information you have now. So they are projecting from 2019 to 20 to
5 or
20
so.
so to 2018.
Oh,
So
wow.
yeah, so to 2018, from 2019 to 2018. That's what they are projecting.
Yeah.
Or what we say forecast, but this is a lot.
Right.
So, but you
All
can
right.
do that, but yeah.
Okay, thank you so much. So sorry for waking you up this early and I mean using your energy for 2 straight hours. We're very grateful. May God continue to replenish you. Thanks for your contribution. Thankfully, this is recorded, so we're always going to be able to refer to it. And for everybody who has attended, thanks a lot. BMA is Black in Maths Association, and our deal is to give Black mathematicians a platform wherever you are on earth. It's not only for Nigerians, we have people from everywhere, and we are still expanding. So, and this webinar is we do this quarterly. We also have other programs like View Space, where we interview very older people who have been in different fields of mathematics over the years. So just stay tuned. I mean, as you also join our community, maybe through signing up on the website, you can also find some information that will be helpful. So the next webinar should come up anytime from maybe sometime in May or June. So just watch out. We'll put the flyers out also. So brace up for another very interesting time. Once again, Dr. Kayode Oshinubi, thanks a lot for this great. We are very grateful. All right. So at this point, we can call it a day. It's been a nice time here. Thanks for attending. Thanks for being part. See you later. Somewhere. Thank you. Bye.